Good morning, all the participants. So the session will start in 5 minutes. So good morning, Joshi sir.
Sir, very good morning, sir. Is my voice is audible to you?
Sir, voice is clear, sir.
Right.
Sir, shall we test the PPT sharing, sir?
Yeah, I do that.
Yes, thank you, sir.
Blissful morning to the respected dignitaries and faculty members. A blissful morning to the respected dignitaries and faculty members. Myself, Sridipti, pursuing third year from the Department of EEE from SV Colleges. Welcome to the short-term training program on research trends in renewable photovoltaic system and its research challenges. I take the pleasure of inviting a man of distinction and a fountainhead of illuminating ideas, Dr. K. Sudhir sir, HOD of EEE Department. Welcome, sir.
Thank you. Thank you, Deepti. It's my honor to have today's session taken by Joshi Manohar sir, an eminent professor from President's University. Hope it will be a real session which will be used for different
University nominee of NISP Implementation Center of AICTE at Presidency University. He has received his BTech in Electrical and Electronics Engineering, Nagarjuna University, Guntur, and his MTech degree in Power Electronics at Visvesvaraya Technological University, Belgaum. He obtained his Doctor of Philosophy in Electrical and Electro Engineering, Jawaharlal Nehru Technology University, Anantapur. Sir has total 18 years of teaching experience in engineering colleges. Dr. V. Joshi Manohar Haru has field of total 4 patents, published 3 books, supervising 7 PhD scholars, guided UG and PG projects. He handled many responsibilities in his career, like Board of Studies member, Department Advisory Committee member, Chair for Technical Session, Judge for National Level Technical Paper Presentation. Sir has organized 16 workshops, published 15 research papers, published 11 international conferences and 3 national conferences. Sir has membership in professional bodies like ISTE, IAENG. Now, I would like to hand over the session to Dr. V. Joshi Manohar Garu. Welcome, sir.
Welcome, ma'am. Thank you very much. I would like to thank management, respected principal and head of the department, and all the persons who are behind for inviting me for this workshop. And though I am not worthy of all your introduction, so it is all a part of journey that we have to carry out through our the part of our work. Anyhow, welcome you all participants for this workshop. Let me give 1 minute to share my screen here. So are you able to see the screen now, which is shared here?
Yes, sir, it's visible, sir.
So as it is introduced, and this is my mail ID. If you have any queries which cannot be addressed in this session, you are free to mail me at any point of time. So coming to the present agenda, today's agenda, I'm going to take the session on control of multi-level inverters using nature-inspired algorithms. And the outcomes of the webinar, that means after successful completion of the webinar, that means after sitting here for 2 hours, the participants shall be able to point after completion of the webinar. The first one is able to discuss the role of nature-inspired algorithms in providing the feasible solution for complex engineering problems. So that means what is nature-inspired algorithms, introduction to that, and why it is necessary, where our traditional numerical algorithms fails, and what is the purpose of going for nature-inspired algorithms. Those points will come to know. The second one is, in order to implement these nature-inspired algorithms, we need some sort of procedure, otherwise setup to implement this algorithm. So in that setup, we need some sort of components in this to formulate this problem. So that is nothing but what are the components of formulating this optimization problem that we will see here. So this third one is divided into two parts. The first one is we will see how particle swarm optimization can be implemented using a single objective function. That means the flow chart, and what is particle swarm optimization, what is meant by velocity vector, how the position will be updated, and how it can be implemented to one problem that we will see here. And after that, we will see how it can be implemented in some application. So this one is divided into two steps. The first one is we will take some numerical example. With that numerical example, we will see how we can implement this basic PSO algorithm step by step. So I don't want to teach this one as a theory concept to you. So we will implement this one in terms of steps here. We will take one numerical problem. Sirisha ma'am, it is better can you mute everybody here? That would be better, I think. Don't mute me. You can mute everybody there. Right. So in this one, we can implement this one using taking a numerical example. One example will take it, and we will see how this algorithm will solve this numerical problem. Step-by-step approach we will see here. And the last one is, I will take one multi-level inverter, which is usually used in medium voltage drive applications. So that multi-level inverter, how it can be controlled with help of particle swarm optimization technique, that we will see. So these are all the takeaway points, or otherwise this is the agenda for today's webinar. The first one is the role of nature-inspired algorithms. Second one is the components to formulate this optimization problem. Third one is we will see what is a particle swarm optimization. And the fourth one is divided into two parts. The first one is we will take some simple numerical examples. If you have patience, you can take a piece of paper and you can practice this example, so that it will give you some sort of a simple boost to you to implement for your own research problem. And the last one is I will tell you how these algorithms can be implemented in a real time to control the chosen multi-level inverter. So whatever the problem, that means the queries that we are having, so we will have a sufficient time at the end of the session. So please note down the slide numbers and everything. If you have any problems or otherwise queries, I'll try to address that one at the end of the session here. So first one is, and by whenever we come across these algorithms, let us say the nature-inspired algorithms or evolutionary algorithms or swarm intelligence algorithms or numerical sum computations, this one, they will act as optimizer. Optimizer means, that means suppose if you're having some sort of a function, finding out of a minimum value and maximum value, not about finding out of minimum and maximum value, there will be one optimum value, which may not be exactly minimum, which may not be exactly maximum. So that is the point where we are concentrating with help of these optimization algorithms. So usually what they think is we are finding out of minimum value of a function or maximum value of a function, but actually practically we're not doing so. We are, with help of these nature-inspired algorithms, we are finding out of the values which are near minimum and near maximum. That is a word that we have to use here whenever we come across the algorithms. But coming across these traditional techniques, let us say some deterministic approaches or gradient-based approaches, they will give you exact minimum values and maximum values. But here, when we come across the nature-inspired algorithms, when we come across one problem where it is difficult to find out minimum value of a function, maximum value of function, I will tell you a number of examples where it will be helpful for you in electrical engineering, not only in electrical engineering, in all disciplines of engineering. I will tell you in coming slides. There, I would like to tell this point very clearly to you is optimizer means it is not a finding out of exact minimum and exact maximum. Somewhere down near maximum, near minimum value, which is optimal value for your function itself working as an optimizer. So that is why the so many innovations came into existence just by mimicking the nature. So that means if you see some foreign universities or across the globe, we are having a biomimic laboratory. That means so far the better innovations came into the existence just by mimicking the nature. So anyhow, even if you see our human structure, our hand and our nose, the length of the nose is nothing but one optimal length we can have. Some hand's length is also optimal length. The finger's length is also optimal. It is not max length. It is not minimum in length. So God has designed in a such way that it is having some sort of optimal in nature. Similarly, if you look into the nature, we can see so many solutions for your complex optimization problems of your engineering. So let me see, suppose the algorithms or otherwise the process of mimicking the nature is nothing but the nature-inspired algorithms. These nature-inspired algorithms are broadly two types. One is evolutionary-based algorithms. I think the popular one is genetic algorithm. I think you know that one. And second one is swarm-based optimization. So all these algorithms, BSO or batch algorithm or honeybee optimization, all these algorithms will come into these box. So nature-inspired algorithms means broadly you can understand here, this is inspired by the nature. That means whatever the design or whatever the process that is present in the nature, if you can able to mimic that one with help of some sort of algorithm, then we can call that one as a nature-inspired algorithms. So then what is the purpose of imitation? That is the next question here. The main purpose of imitation is where your traditional algorithms will fail to provide a solution. That is a thing here. Where your present approaches, gradient-based approaches, iterative-based approaches will fail to provide some sort of solution to you, then what we have to do? We have to borrow some sort of intelligence from the nature. That is nothing but the nature-inspired algorithms. So that means the main purpose of that one is where your traditional based of approaches will fail to provide a solution, then we are going for the mimicking of the algorithms. That is the purpose of going for imitation of all the algorithms here. So next one is what is meant by optimization. I tell you, optimization is either the process of minimization and maximization actually. But strictly, if you see into in another sense, with help of these nature-inspired algorithms, we are not finding out of exactly minimum, exactly maximum. Near minimums and near maximums, we are going to find out of this one here. You can see here, there are so many things we have. Suppose if you want to find out the shortest route, let us assume, if you want to go home from our colleges, we usually find of the shortest route, the optimal route we will consider here. In design aspects also, we consider optimal design. And in the case of manufacturing, we have to produce the product in a such a way that more profit has to come and the cost value of that one should be minimum. So like that, we can see so many things here. You can develop a motor with the minimum cost and maximum efficiency. Like that, you can see here. You can see here one example I'll tell you in another slide here. You can see this is the bird called a kingfisher bird. So the beak of the bird is completely mimicked here in the bullet train in the Japan here. So this innovation came into the mind of the Robertson. He was the who has designed the shape of this bullet train in this way. Usually, I think you know that Japan is completely filled with these mountains. So you know already this bullet train travels with this higher speed, I think 300 kilometers per hour, 400 kilometers per hour, something like that. So by the time when this train enters into these mountain caves and coming out of that one, it is making so much of noise. So all the people who are surrounding by that mountain places, they gave a complaint to the authorities to solve this one here. So out of frustration, this Robertson, he went to some geographical park for his outing. There he found that this bird is catching the fish without making any noise. That means even the noise That means the moment when this when it tries to catch that fish, there will be some sort of displacement of the water, right? Even that the water displacement is such a way that cannot be noticed by the fish. So that principle he has understood. That means he is catching the fish in a such a way that even the noise of displacement of water is not noticed by that particular fish. So he has understood that one, and he has mimicked the same shape here. That means there the water displacement is not making noise. Here what happened, no, when it enters into that caves, no, it is not making any noise here. That air displacement will be there, no, sucking of air and again blowing of air won't be there here. So that means he has mimicked the shape here for some problems. That means the nature is helping us to give some sort of optimal solutions, better solutions for better innovations for our problems here. We can see here these wind turbine blades. These wind turbine blades are just mimicked by the wings of this whale here. You can see here, this is the shape of the whale here. So if they have mimicked this one for the design of this turbine, wind turbine, then what happens now? They have observed there is a reduced wing drag and there is a 40% of improvement of wind turbine. So that means these are all the optimal solutions. One cannot design your wind turbine simply like that. So this is optimal design. They have copied from this whale. Similarly, I think you have seen this one here. This is a B2 bomber. So then you can see here, this shape is exactly same or mimicked by this falcon bird. So the falcon bird has inspired the US engineers to design this B2 bomber. So the main point I want to emphasize here is the nature is having some solutions. It is some people who have caught that one to have a better solutions here. We will see in detail here what is the purpose of optimization. We'll go to the second objective of our this one here, and then we'll go further here. I think you can see here the mobile phones. Initially, the mobile phones size was like this, and now we are using this size. The cameras, like this, and if you see the computers, initially they were like this, and nowadays we're having computers like this. That means what is the motivation behind this evolution is nothing but the optimization only. That means we have to produce a device with a less cost, less weight, and with optimal design. So the inherent philosophy behind all these processes is nothing but the optimization, optimal design, optimal design of materials, optimal design of that means cost, minimum cost, maximum profit. So that means these are all optimization only here. Next, we will see the terminology before going to the algorithm. Unless we know this terminology of this one, it will be very difficult for us to develop one algorithm here. First one is what is optimization. I have given already introduction for this one. So you see in a broader way here, what we are doing here is we are finding out of some certain set of decision variables. That means some variables will be there in the problem. Maybe switching angles, maybe whatever it may be, optimal scheduling of your generators, or finding out of a duty cycle. I'll tell you later when coming to the applications here. So there will be some variables will be there in your problem. You have to find out the variables in such a way that your objective function will be either minimization or maximization. That means there will be some objective function. The objective function will be formulated with the help of these variables. So you have to find out in such a way that these objective function, either we have to minimize the objective function or otherwise we have to maximize the objective function by satisfying the constraints here. So I think here I have used 3 words here. One is objective function. I will tell you what is objective function just by taking the real-time example, which we usually do, making of a coffee. I will take a simple example, which really like that example to explain this particular concept here. Second one is the constraints that I will tell you. And another one is the variables here. So that means the 3 words I want to tell you here. One is the objective function. The second one is the constraint. And the third one is the variable. Don't get confused with the help of this terminology. But I'll take you one example so that you can understand it in another way here. coming to the maximization, so many things you can do, right? Efficiency can be maximized. You can design a transformer, and the profit should be high. Optimal power flow in the transmission line should be a maximization. Coming to minimization, the losses should be minimized. Noise in designing of running of a motor should be less. The cost of that one should be less. The percentage of that one should be less. Produced by this inverter should be less. And the size of the filter, maybe size of the motor should be less. So there are so many things we can correlate that one depending upon your research example here. Coming to the constraints, constraints will depend upon problem. What is constraints? Then I'll tell you later here. So anyhow, this is the important point. Optimization is helpful in tuning the knowledge into decisions, because after developing some algorithm or otherwise finding out of optimal solution, what is the purpose of knowing those solutions? That is nothing but to take a decision, here. So that means optimization is inculcated in day-to-day life. Maybe where we have 24 hours time, that is a constraint, let us say. How best we are utilizing is nothing but optimization. We have priorities, and we will schedule our everything according to that one here. So anyhow, we can use several examples to understand this this one here. Let me see the optimization thing here. Suppose if you see electrical engineering, I will list out some few examples. You are not hearing something new. Suppose if you want to develop something, should be optimal power flow. There we can use these algorithms. Economical load dispatch problems, commitment problems, you can use that one here. Operating a power plant with less emissions and the placement of capacitor banks, then we can use this algorithm here. So maximum power point tracking, finding out of a duty cycle, you can use algorithm here. Tuning out of KPK values in control systems, you can use these algorithms here. Inverter control that I'm going to tell you now how it can be implemented, you can use these algorithms here. And operating a machine, finding out of optimal condition to produce higher efficiency, I can use this one here. And recently, one of my scholar is operating using the same algorithm, and he is finding out of optimal diameter of the void which is present in the transformer to initiate at PDIV. So there also you can find out optimal diameter of the void. You can use these algorithms here. So it not only this area, it is interdisciplinary. Nowadays, everybody is running of data science and machine learning algorithms. There, in order to tune certain parameters to fit into data, pattern recognition, we are using these algorithms. Not only these algorithms, that means not only PS, all algorithms can be useful here. Particularly in mechanical, I think straight away we can tell design problems, material selection problems, what material that we have to select, everything we can use this one here. Coming to the automotive electronics or automobile industry, we can use these algorithms here. Particularly, suppose if you want to reduce the noise of an engine, because if you see some cars, they are producing more engines. If you see tractor that's producing more engine when compared with some other cars, that means noise reduction is also one optimization problem that can be addressed with help of these algorithms only. Noise reduction in closing the door. Recently, the Tata Motors, they have launched one vehicle. Then after launching the vehicle, they observed that by closing the door, it was making so much of noise. So again, they have taken back that particular car and they have worked on reducing this noise while closing the door. So that means what I want to tell you here is there are so many areas where we can use these algorithms, not only in electrical engineering, it may be applicable to your own research problem, but you can use this one as a blueprint or some sort of structure to develop your own model here. Let me take you some sort of simple example, and so that you can understand this terminology in a better way. Just now I told three terms there. One is objective function, variables, and constraints. All your optimization problems revolves around these three things. Objective function, development of, if you can develop objective variables, if you can, that means you can identify the constraints, and if you can develop objective function, 80% of your research problem is over. So that means all the thing what you have to do here is, for your problem, you have to identify the variables, constraints, and using variables and constraints, you have to develop an objective function. Let me take this example here. You can see this example. There are two figures I am projecting here. This is a case study. This is not my thing here. This is a case study here. The thing here is this case study of coffee composition. Here, these people are called coffee tasters. Their duty is just to come and sit here, and they have to taste these different coffees, and they have to produce a report. For that, they are paying a huge money here. What happens here is, what is the coffee composition? Here, what they will do here is, you can see here, they will take coffee which is available in India, they will take coffee powder which is available in Sri Lanka, they will take coffee powder which is available in Italy or some other countries. So they will take like this, let us say 1, 2, 3, 4, 5 countries, the coffee powder that is available, and they will mix it with different compositions. Let us say at one case, this India will be 10% or another one will be 5% or 3%, something like that. They'll use different composition. And using different composition, some coffee taste will come, no? So that coffee taste will be tasted by these coffee tasters, and they have to produce their report here. So understand this one so that you can understand your optimization problem so simply. Let us assume, I think everybody is familiar in preparing of a coffee. So in order to prepare a coffee, let us assume we are preparing coffee here. Suppose if you are preparing a coffee here, we need 1 cup here. Let us say that is in terms of ml. And another one which you need is sugar. Let us say that is sugar is needed for you. Sugar is needed. And the third one is the coffee powder. So these are the, and another one is milk also. You need milk also. So that means you need a cup here. That is the first thing. And another one is a sugar you need, and another one is coffee powder you need, and another one is milk you need. Now let me understand these 3 things here with help of this example. Let us assume you are preparing a coffee. I would like to ask you one question. There is no guarantee that unless your compositions and everything are right. I am not telling about Saravana Bhavan coffee or Adir Anand Bhavan coffee. They have a fixed taste. Whenever you go and sit in the you will get a fixed taste. If you taste coffee in your home, then you will. That means one day you have one taste, one other day you have another taste. That will be there. So that means if your taste of a coffee is varying, then please remember that you are in home. Suppose if the taste of your coffee is same, that means you are in a hotel in your home. So obviously taste of preparation of coffee from your wife or mom obviously varies. So let us take example here. Because we are preparing coffee, not a coffee shop. There is no guarantee that. There is no guarantee that it will produce same taste. Same thing. There is no guarantee that it will get same rhythm. You got point here. Also, suppose if you are preparing a coffee, there is no guarantee that you will get some exactly same taste every day. Same thing, your algorithms which we are developing now, there is no guarantee that every algorithm, every time when you run the same algorithm, there is no guarantee that this algorithm will produce the same result. The objective here is to produce a coffee, to prepare a coffee with better taste. Better taste. That means best taste so far in your mind. It was already listed in your mind. So that means your objective function here is that taste. Taste should be high. Maybe in your problem, cost should be minimum, or power flow should be maximum, or a percentage THD should be minimum. So like that, your objective function will be there. Here in the preparation of a coffee, so the main thing is my taste of coffee should be maximum in taste. That means beautiful in taste. That is the first thing here. Next one is variables. Variables. I think now we can understand variables here. To prepare a coffee, what are the variables? Can you please tell me? The first variable is milk. Milk is one variable, and coffee is another variable, and sugar is another variable. That means how many variables are here? 3 variables are here. Is it right? So that means your objective function is taste here to produce a better taste, I can write here better taste. I don't use the word best because there is no best algorithm. So I want to produce a better taste, not best taste. Whenever you are writing a paper or something like that, don't ever, never ever use the word best like that. It's a better one. So similarly here we are having a 3 variables here. The first one is sugar, second one is a coffee powder, and third one is a milk here. And next one is a constraint. You want to understand the word constraint here. What is a constraint here? Constraint means constraint is having some limits. The word constraint means I'm having some constraint. That means I'm having some limitations. So suppose if you ask me to fly, I cannot fly. I'm having some constraints. So in a similar way, suppose if you coming to a milk is having some constraints. So how much of milk it is required to prepare a coffee? Do you need 1,000 ml of milk? Do you need 2 liters of milk? No, it's not like that. It is in terms of ml. How much milk you will take here? Let us say the limits of that milk is maybe some 150 ml to 200 ml. Let us assume. That is the limits of that one, depending upon the coffee's cup size and everything. Similarly, what will be the coffee powder? Some will take light coffee, some will take strong coffee, some will take medium coffee. That means it will be in terms of 1 teaspoon to 2 teaspoons or 2.5 teaspoons. 1 teaspoon to 2.5 teaspoons. Similarly, if you take sugar also, some people they won't take sugar. Those who are having sugar, they won't take sugar. Let us say from 0. And some people they use more. They will take more with more sugar. So let us say 2 teaspoons or 1.5 teaspoons. So now can you see here, I have clearly defined all these things here. Objective function is a better taste. I think you can understand the word here. These components are very, very much is important for you to understand here. Second one is variables here. Variables means variables in your, suppose you are controlling inverter to produce a minimum percentage THD. There the variables is alpha 1, alpha 2. Suppose you are optimally scheduling your generators, the variables are generators. You have to find out which generator has to be operated. Similarly, coming to the constraints here, these are the constraints here. Constraint for milk is, that means 150 ml to 200 ml. So that means that is constraint. Minimum is 150 ml, maximum is 200 ml. Constraint for coffee powder is 1 tablespoon to 2.5 tablespoons. That is a composition. And combination of sugar is 0 teaspoons to 1.5 teaspoons. Now you see here, every time you prepare a coffee, at one point of time, you may take 1 tablespoon of coffee powder, 1 tablespoon of milk, 1 tablespoon of sugar, and maybe 180 ml of milk. Then if you taste it, that taste may be different. Suppose if you take 1.5 teaspoon of coffee powder and 2.5 teaspoons of sugar and 100 ml of coffee powder, then if you taste that composition, that taste will be different. That means the variables are varying from 150 to 200 ml in the case of milk, and 1 tablespoon to 2.5 tablespoon in the case of coffee powder, 0 teaspoons to 1.5 tablespoons in the case of milk, in the case of sugar. That means when you run your algorithms, if you know the variables, you will get variables in this range. Your constraints is having some range, right? Minimum value and maximum value. Whenever you run your algorithm, you will get some variables here between these two, satisfying these two. So the thing here is, every time you run an algorithm, you will get a solution. All solutions may be a feasible solution, but may not be optimal solutions. That is the point you have to understand here. So let me summarize your second outcome today. The first outcome I told what is the necessity of these nature-inspired algorithms that I told. That is the first outcome I expected that I should know. The second one is the components of your optimization problem. Components is very simple. Objective function, I told you the taste of your coffee. The variables which are present in this coffee preparation or sugar, coffee and milk. And constraints of the variables. Variables is having constraints, not your objective function does not have any constraint. Please remember that one. Your variables is having some constraints. So your variable, that means your objective is to find the set of variables which will satisfy the constraints in a such a way that your objective function may be minimization or maximization. I will repeat the statement once again. Your objective here is, in all your research problems, whatever it may be, your objective here is to find the set of variables. Those set of variables should satisfy the constraints. That is another thing. So these constraints, when you substitute in this objective function, it has to give some sort of task, maybe minimization or a maximization. So that is a thing that we can understand here. So let me go further in our discussion here. So these are all the things. There is no need to read again this one here. Objective function, just now I told. Objective function is a function to be minimized or maximized. Then what is a variables here? Variable set of unknowns. Just now I told that sugar and milk, and another one is the coffee powder. So this will affect the value of objective function. That's important. How it affects the value of objective function? It may be a minimization or maximization. So let me go further here. Constraints, just now I told constraints. Constraints is nothing but set of constraints that allow unknowns to take on certain values but exclude others. So that is some constraints definition here. Right, let me see how it can be implemented here. I will tell you in simple 3 steps. First one is you have to develop objective functions with optimization algorithm. That is what I told here. There is no optimization algorithm because some researchers they have done research on that is called no free lunch theorem. That is NFL theorem. It states that suppose they have taken some algorithms. Let us say the problem, we are having one problem. Let us say one optimization problem. Let us assume, and they have used 3 algorithms, ABC algorithms. They observed that on an average, more or less all these algorithms performed well. Maybe some specific cases, some algorithm may be superior when compared to other algorithm. So what they observed that is there is no good algorithm and there is no bad algorithm. There is no worst algorithm. So for an optimization problem, for your research problem, one algorithm may produce better results when compared with another algorithm. That thing may happen. Suppose in my case, I applied 2 algorithms, 3 algorithms. In 3 algorithms, one algorithm has produced better results when compared with another algorithm. It doesn't mean for all optimization problem, other algorithms are producing bad results. It's not like that. So that means if you start the research, what you have to do is we have to take in optimization algorithms. You take algorithms, preferably starting from the numerical algorithms and some optimization, some swarm intelligence or evolutionary based algorithms, and you start comparing that one. So then only that means the better algorithm will come, not best algorithm. There is no best algorithm. So this is the important point that we have to remember. That means you have to find out for your objective function which algorithm is suitable. That you have to know. And another one is the algorithm should have robustness. That means it should have some good performance. And obviously the time factor will be there. If it's taking more computational time, then we don't have that much of patience to find the answers. And accuracy should be there. And but these algorithms, each time when you run here, there is no guarantee that it will produce the same results. It will produce some better and different results it will produce. Next one is validation. So these are the steps of implementation of any algorithm, maybe PSO algorithm or ABC algorithm or XYZ algorithm, whatever it may be. These are the 3 steps here. The first one is objective functions you have to find out, variables you have to find out, and constraints you have to do. So then I don't want to waste time here. Suppose if the objective function is having only one variable, that is called a single variable. Suppose if in a simple example, if I take the efficiency of a transformer, if you consider the variable is secondary current I2. So the multivariable will be there. That means number of variables will be more. Constraint means, just now I told constraint, constraint means the minimum and maximum limits are there, for coffee powder and everything. That is called constraint. If there is no constraint, non-constraint also. The objective function is only one theme of doing thing, that is called single objective. Sometimes multi-objective will be there. So these are the things here. Now let me see clearly about these techniques here. A little bit, you please pay a little bit of concentration. Now we can understand this one here. Let us say the function is like this. I think you know this one is a sine wave or a cosine wave, whatever it may be. So the philosophy here is, suppose if you reach this point, let us say and A, or let us say the point B. If you reach either of these 2 points, then what is the gradient here? There is no gradient at this point. That means gradient is 0. Suppose if the point is here, let us say it is having some gradient. If it is having some, here also it's having some gradient. Here also it's having some gradient. The points C, D, and E is having some gradient. But the point B and A does not have any gradient. That means, suppose if you are solving one problem in your research problem, when the gradient vanishes, that means when your gradient has vanished away, I think either you may reach your maximum point or minimum point. So your traditional gradient-based optimizations, let us say the familiar one is Newton-Raphson method, it is a gradient-based approach. The moment when the gradient ceases, no, it will stuck either in the minimum position or in the maximum position, depending upon your objective function, how you are solving the problem. So all these gradient problems, what happens now? They will always search for this minimum, and once they reach this minimum, then they won't. Suppose, let me tell you, one objective function is like this. Let us say the objective function is like this. If the objective function is like this is one minimum point, this is another minimum point, this is another minimum point. Let us say this is E and F and G. Let us assume this is one objective function, this is one objective function, this is another objective function. In this objective function, what is the minimum value here? G is the minimum value. G position is the minimum, no? So, but if you start your gradient approaches like this, then it will stuck at this point E. They won't explore this place, such place here, such space. Your such space is having somewhere down the line at G, you are having a minimum value, but your gradient based approaches, no, then it will stuck here. So that is the main drawback of these problems here. If you see here in this problem, this is one objective function like this, Here we are having global minimum. Suppose if you are using these optimization algorithms, traditional gradient based algorithms, they stuck here because the gradient stops now here. Suppose if they start from at this point, it will ended up here. It won't go to such where is a minimum position in this such space. They won't do like that. That is the limitation of these algorithms. That is why we are going. It may be a minimization because I have taken minimization problem. It may be a maximization too. Maybe it may be like this maximum point algorithm in your MPPT algorithm. There it is operating on this gradient approach only. So that means when the gradient reaches, this is a more point, that is a more maximum point, global maximum. And this is not global maximums here, right? These are all local maximums here. So this is a global maximum here. Here, this is a global minimum here. These are all local minimums here. These algorithms, what happens now, if you, all these Newton-Raphson method, I think you might have studied in your BTech also. You need some initial guess, starting point. Initial guess is required. So if your initial guess is this point, then you stuck here. Suppose if your initial guess is right, then you landed up with exact solution. Then what is the probability of guessing initial guess all the time? Good initial guess all the time? It's not possible. So then we go for these nature-inspired algorithms. So coming to, this is the backdrop of these going for these nature-inspired algorithms. That is a limitation. So one should not feel that everybody is doing this algorithm, that's why I'm going to this algorithm. Not like that. You just, suppose if you take a problem, you apply nature, you apply this traditional based approach methods, then you will get drawbacks of that method. Overcome those drawbacks, better you go for this algorithm. That should be the flow of your work. So these evolutionary algorithms, that is one setup, genetic algorithms, differential evolution strategy. So some algorithms are there, you can search it out. And swarm intelligence means ant colony, artificial bee colony, batch algorithms, Beowulf optimization. And here we are doing these particle swim optimization methods. So these are all, this is the one broad classification of nature-inspired algorithms. Evolutionary based, and another one is the particle, that means swarm intelligence based algorithms here. Let me see here. This algorithm, we will see what is these algorithms. I will tell you, and using this one, we will try to solve one small numerical problem so that you will come to know how this algorithm is converging into a local minimum, or how it is converging into a global minimum, that we will see here, finding out of some minimum value which we already know. So the beauty of this algorithm is this is a very simple algorithm. That is the first point. Coding is also very less computational time it will take. And ruggedness means you can check whether for your problem it is rugged or not. But here it is rugged, for this problem it is rugged. And another thing is, this was developed by some electrical engineer. So being an electrical engineer, we should have some sort of soft corner about this algorithm. And these are the two professors. I don't want to give details of reading these names or something like that. We are more concentrating about how it can be implemented. Anyhow, Russell and Eberhard, Russell C. Eberhard and James Kennedy, these two people were behind this development of this algorithm here. So first, the point that we have to understand here is, this is inspired by the social behavior of bird flocking. That means, depending upon how birds will search the food in the search space, they have mimicked that algorithm. There are 2 points that we have to understand about all these algorithms here. In order to understand this one, I will tell you one example. Suppose if you want to buy one mobile phone here, then if you want to buy one mobile phone here, what you will do, you have some requirements. Let us say my specification should be like this. Some RAM should be like this, some hard disk, that means that memory storage should be like this, or whatever it may be specifications. Clearly don't know about what that specifications are. Anyhow, some specifications will be there for that mobile phone. And then what you do, you search ads, and which mobile has reached, that means launch, and you will search that one. And also you will ask some other person also, so which mobile is good, and then you will take a decision. That means if you see here, please understand the two main pillars of these algorithms, whatever it may be the algorithms, maybe ant colony or ABC algorithm, whatever it may be. The main 2 pillars is, one person is having self-intelligence. That means you are having your own intelligence, your own memory, let us assume. And you are getting some sort of information from others. That means you are asking other person which mobile is good, something like that. That means you are taking information from others. That is a second point. The first point is, you are having your own expectations or own memory. By considering those 2, you are taking steps. Listen very carefully. That means you are having your own memory, first one. You are taking information from others, second one. And coming to taking these 2, you are taking the third step called a step. That means your position you are updating. The beauty of these algorithms is, you are having your own best, that is called personal best. You are getting some information from others, that is called global best. By using the personal best, by using the global best information, you are updating yourself. Updating means, what you are updating, you are moving. Let us assume somebody has told the mobile phones are good in some other mobile. Let us say some showroom it is good. Then what you will do, you will go. You will go means what you do, your velocity is updating, your position is updating. So with help of this example, I have identified some parameters here. What are the parameters I have identified here? One is P best, one is the personal best, and another one is G best, that is called global best. And the third one is your velocity is updating and position is updating. That is what we are doing in these algorithms. So simple as simple as that. So then another thing is, all these algorithms, they need some sort of population. Again, I tell you one example so that you will understand what is a population-based search. These are all called population-based search algorithms. These are all called stochastic algorithms. Those are all called meta-heuristic algorithms. All these names are similar only, same only. Then I'll tell you another example here. So another example here is, let us assume you are playing some sort of hide and seek game. Let us assume you are playing some treasure hunt game. Let us say treasure hunt game. So let's say some 1,000 square feet flat is there. in that 1,000 square feet flat, and then you have placed one gold coin there. Let us assume some gold ring you have placed somewhere in the corner of the room. Let us assume, and you have informed one person to search it out where it is present. Okay, then the simple question here is how much time it will take for a single person to search for that ring? Because only single person is searching that particular thing. Obviously, it will take more time to search it. Instead of that, suppose if I take 50 students, let us assume 50 students, and I gave order to 50 students to search for the same ring. So that means everybody has started their search. Then one person and another person is sharing the information. That is the important point. You please share the information. Whenever it is not present, you please share the information. This room it is not there. That room it is not there. That means, let us say if 2 to 3 rooms are present in that flat, then 5 members, they may enter into that flat. They pass the information. In this room it is not there. That room is not there. Then immediately, collectively, you will get one information. One person will tell you, I found this one here, like that. That means if more persons are there in this search process of finding out of whether minimization or maximization process, your computational time reduces. But the philosophy here is what you have, and you have to update the information to others. That is called sharing the information. And also you should have some cognitive level. You have some sort of intelligence to find out that one here. So what is this particle swarm optimization? Particle swarm optimization means it is, I told you, it is inspired by the birds, how it takes its food. So this process of taking food depends upon two parameters, important parameters. One is communication and another one is learning. This is very, very important. Anyhow, this philosophy will be helpful for everybody if you want to update ourselves. So if we want to find the solution, better solution here, these birds, whatever the birds are there, which they have observed, the persons who have developed these algorithms, who have observed this one, they observed that they are communicating with themselves. That is the first point they have observed. And also they are learning. They are learning means one bird will go to one place and they will tell and will search their food for that at that place, and it will pass the information to other bird telling that food is not present here. Then that bird also will share the information. Yes, food is present here. Mutually they will share the information and then they travel like that. So that is how the important philosophy in any algorithm, nature-inspired algorithms is, first one is learning. One has to learn, and another one has to communicate with each other here. Let us assume here, I'll take one example so that now you can understand this algorithm in a better way. Then we will develop these two equations. Only two equations will be there. If you know just very simple equations, then you can solve any research problem of your own choice here. Let us assume there are two persons are there. Let us say this is a person A and this is person B. So the person A and person B, they both want to catch the fish. Let us say then what they used to do, self-learning. This is called self-learning, right? Self-learning, they identified that they didn't find any fish here. And what is the next step that we have to do? They have to pass the information, right? Communication. So this person has communicated first. So this person has communicated to this person telling that I didn't find any fish here. Similarly, the second person has started, second person has started his communication. Yeah, he started his communication. So that means the two process I told, one is self-learning and communication has done. So after that, you see here what they are doing now, because they didn't find any fish here, then they have to continue their hunt. Then what they have to do? They want to change the position. So if at all they want to change the position, that means if you want to run to move one place to another place, we need some sort of velocity, right? So that means with velocity they have moved from one position to another position. Let us say this is third position, and let us say this is the fourth position here. This is the fourth position here. So this person B has reached the fourth position and communicated to another person telling that I found fish here. Then another one is, he also did the same thing. And I am present at the position 3, but I didn't find anything here. Then what this person has to do? So because the fish is present here, this person immediately move forwards in this direction. This is how the birds will catch their food. That means they're in a swarm, they're in a group. Each group is having potential to find the solution. This is the point you have to remember in your algorithm. Suppose in your algorithm, there are so many variables are there. Each algorithm, each bird, each particle is having a potential to find each bird is having a potential to find the food. We never know which bird will find the food. So we are giving equal opportunity to everybody to find to perform better. That is not happening in your genetic algorithm. Genetic algorithm is nothing but survival of the best. Suppose if you are not performed in one iteration, you will be discarded in the iteration. That is what we are doing in the genetic algorithm, survival of the best, survival of the fittest. If you are not survival in one iteration after crossover, then you will be no more in the next iteration. But it's not like that in this PSO algorithm. It gives some equal chances when compared with the genetic algorithm. So this is the philosophy here. So what is the first step we have to do here? The first step is the personal best will be there, global best will be there, position will be there, and velocity will be there. So can we see how it can be implemented here? This is the nomenclature I already told you. What is the nomenclature I told you? I told you already P-based. What is P-based? I told you. P-based I have already told. What is the G-based I have already told. G-based is nothing but the minimum position or maximum position for any particle. And because for everything there is a such area. Such area means, suppose if you see switching angles, let us assume the constants of the switching angles, maybe if you assume 0 degrees to 90 degrees, what is a such area here? Whatever all the angles present between 0 degrees to 90 degrees is nothing but such area. Those are all possible solutions for your problem. Suppose in the preparation of a coffee powder, 1 teaspoon to 1.5 teaspoon, between 1 teaspoon to 1.5 teaspoon, whatever the such space is there, that is called all such space. So whatever parameter, maybe 1 teaspoon is a possible solution, 1.5 teaspoon is a possible solution, 1.25 teaspoons is a possible solutions, like that. So that means these are the nomenclature you have to understand here. I think you are very clear with this nomenclature. B best means the personal best of a person. G best means the global best of a person, of any that group or something like that, maybe bird, something like that. And we are going to find out global optimum. Global optimum may be global minimum or global maximum, whatever it may be. And each particle is keeping a record. What is the record it is keeping? It is personal information it is keeping. Best value of any particle, total particle you are viewing. So how it is moving, that we will see with help of equation here. And then we will go to algorithm here. This particular thing I have already example I have already told here. So this is the mathematical modeling is very, very important here. Let me tell you this example. It's very, very simple and easy to implement here. Let us say this is xi of t. This is the initial position here. This is the initial position. Vi of t is the velocity. Remember, it's very simple here. This is initial position, let us assume. Initial position. It is simple mathematics only. We are getting two equations. I told you, what is the two equations I told? One is velocity we have to update, and another one is position we have to update. Velocity means v, position means x. So this we have to update at the end of the total this one here. So you see here, I told this one is having some personal best information. For any particle, it is having some personal best information. So this personal best information is nothing but PA of t. Is it clear for you? This is the position of a particle. For a particle, it is having some best position in his mind. That is called personal best. That is called P best. This is the P best for this one. So P best. And similarly, for entire swarm means for entire group of birds, there will be global best. Similarly, in a classroom also, if you see here, one person will be topper, maybe two persons also will be topper here. Let us assume one person is topper. So for entire class, one person is topper. So like that, we are having a G of t. This is called a global best. This is not a vector here. This is a value. You got the point here. So next one is, there is a vector connecting these 2 points. Let us say this is x1, x2, y1, y2. I think you know equation of a line. Similarly here also same thing. This is pi of t and this is xi of t. The line joining these two is nothing but pi of t minus xi of t. This is the line joining between these 2 points. We are representing everything in a vector here. Pi of t minus xi of t. Similarly here also, this is a global best position, right? This minus this one. This is nothing but the line which is connecting between these two. Now we have to update. What we have to update? That is the question here. So how we will update here is, initially it is starting to move in this direction. This is a velocity VA of t. Okay, so then it will start moving parallel to the personal best, because the personal best is there now. So there is a vector which is parallel to this one. Using a parallelogram, we usually do that one, no? In vector finding out of line values, line voltage values in a star connected generator, something like that. The same thing, parallelogram, the line which is parallel to this one here. This is a parallel one. So this vector is nothing but, I think you know what is this vector. This is pi of t minus xi of t. Then it will start moving towards the global best. Actually, it will start moving towards this one. So that means a line which is parallel to this one. There are three steps that is taking place here, because we have to update, no? In the similar way, the person has updated himself. He started moving in the same direction. I think you can see here. The first person, he started in his way. Initial velocity is having some initial velocity. Then after that, what happened? He has seen the best position in this process. Then he updated. Initially, he wants to prove in a such a way that his personal best is good. Then after that, he observed that when compared to his personal best, the global best is good. This person's performance is good. That's why this person has updated himself towards this person. The same thing here. So initially he started in this way, that is VI of t vector. And he want to give his best. Let us say this is personal best. This vector is nothing but PA of t minus XI of t. Then he started towards the global best. The global best is like this, parallel to this one. This parallel to this one only. This started in this way means parallel to this one here. This vector is nothing but, what is this vector? GI of t minus XI of t. So the summation of the vectorial sum of first one, the vectorial sum of second one, the vectorial sum of third one is the resultant here. This is the resultant here. See here, this is the resultant here. So it is very simple. So Vi of t plus 1 is vectorial sum of three components. I told you, the first component is V of t. So this is V of t. Please take snapshot of this one. It will be helpful for you to solve one problem after that one. Vi of t. Then the vectorial sum of this one, second vector. What is the second vector? Pi of t minus xi of t. These are all the things that we will tell later. Pi of t minus xi. This is a vector here. And second one is this one. Third one is this one. What is this one here? G of t minus xi of t. So G of t minus xi of t. So this is C1. There are some parameters that we have considered while formulating the equation. This is weight. This is weighting factor. In order to have balance between exploitation and exploration, I will tell you what is exploitation and exploration. That is a word. And C1 is self parameter, that is called self parameter, and this one is the social parameter here. And then you see here, after finding out of the velocity here, then its position will be updated. So what is the position here? New position here. What is the new position here? Xi of t plus 1. Xi of t plus 1 is nothing but Xi of t, this one, initial position, plus velocity. What is the velocity we got here? Va of t plus 1. Very, very simple equation. Your total algorithm is two equations only. Your total PSO algorithm, that is why it is very simple. So I will explain this one once again. Let us say the position, initial position is xi of t. Now what is the position now? Xi of t plus 1. What is the initial velocity? Va of t. What is the final velocity of updation? Va of t plus 1. How it will be updated? It will be updated based upon initial velocity, the personal information, and the social information. Using these three quantities, new velocity has come. After finding of new velocity, that new velocity, when you add with this initial position, then you got the new position here. So you please take a snapshot of this one. This is very simple, and we will use this algorithm to solve one numerical example, so that it will be easy for you to understand here. And next, I would like to tell the word of, I think you please take a snapshot of this one. I'll take some few seconds of that one. It is very simple. Please take a snapshot of that one. Right. Please understand this word exploitation and exploitation. Exploration means, suppose you are having such space. Let us say if you want to buy one fridge, let us assume. Let us say if you want to buy fridge in some Tirupati, then you will explore total boundaries within the boundaries of Tirupati. What are the showrooms are there? That is called exploration. Suppose if your algorithm is not exploring the total such space in the entire, just like if you're not finding out of what are the best refrigerator showrooms are there in Tirupati, if you're not finding out of that one, so you are not doing best. So that means exploration. That means your algorithm should have capability to find the promising solutions in such space. Then only the better solutions will come. Maybe some better solution, some showroom will be there better in some other area. If you don't find out that one, then you may not get the good product in the same way. Next one is exploitation. Exploitation means you have to discard the inferior solutions and you have to go for the good solutions. Suppose if you find one solution, one showroom is not good, you don't keep on expecting that to give some better solution after some intervals. Maybe after some iterations, you can wait for that some time. Then after that, no, then you have to discard that one. So that means you should have the balance between exploration and exploitation. Then only this is the good nature of inspired algorithms. Your algorithm should have whatever algorithm that you are selecting should have the balance between the exploration and exploitation. Then this is what we have seen here. Vk of +1 is equal to, just now we have a velocity here. The velocity of ith particle in the kth iteration. We will speak every time in terms of iteration here. If you go in detail, you will get confused here. But remember, this is a velocity updation. So C1 and C2, I told this is a cognitive and social parameter. Cognitive parameter means self-intelligence. C1. Social parameter means intelligence that you are getting from other person. So some random numbers will be used here for iteration and everything here. So this is a equation which is required to calculate velocity. And P best I already told you, P best of I particle or P best of that one, everything I told. And what is xi? Xi of t +1 is equal to xi of k, something I already just now I told. Anyhow, these two equations are important equations. Important equation. Then only we can work on the algorithm here. So coming to the flowchart here, it's very simple. All these algorithms, whatever algorithm you name, all they have population. I told you what is the purpose of population. Initialize location. We have to initialize some parameters here. Here, what we have to initialize? You need some sort of population. These are all population-based algorithms, meta-heuristic algorithms. So you need population. So some population you will take randomly. Maybe 1,000 birds you will take, 4 birds you will take, 5 birds you will take. It's depending upon your space and how you want to find out the solution in a better way. That one, for each bird is having some position, right? Because if you see in that catching of fish problem, one person is present at one position. It is having initial position is there. Initial position and also initial velocity is there. So that means for everything what we have to do, we have to initialize the population. We have to initialize the location. That is the first thing. The second thing, we have to initialize the velocity. That is the third thing. And we have to initialize the parameters also. That is called C1, cognitive parameters, social parameters, C1, C2. These are all called algorithmic specific parameters. Please remember this new word, algorithmic specific parameters. The C1, C2, something like that. All algorithmic specific parameters. So we have to define all those parameters here. That is the first step that we have to do. Next one is, actually, we have to calculate the fitness value or objective function or fitness value. So this fitness value you have to find out now. Suppose if you, after substituting all these values, and if your fitness value or objective function is providing you the right answer, then you can straight away terminate yourself for the answer. There is no need of going for the iteration. Suppose if you are not got the right answer, then what you have to do? You have to update the velocity and this one. Just now we have updated now. We have updated the velocity. We have updated the position. Just now with the help of two equations, equation 1 and equation 2. After that, we have to do that one. We have to update the position and velocity like this. Just like in the example, how the fish, the persons who are catching the fish, they updated themselves. We have to update here. Next, after updation, calculate the fitness value. So if it is a value is okay, then terminate that one. If the value is not okay, then again go and repeat the process. And the terminating criteria means maybe it may terminate if you if you are getting the values are good. That is one way of terminating. Suppose if you are having a number of iterations, 1,000 iterations, you can terminate like that. That is you can define that one. So this is a flow chart. Let me put you in a very simple way. First, we have to initialize everything. That is the thing here. First one. Initialization means population you have to initialize. Initial velocity, initial position, C1, C2 values, R1, R2 values, everything that we have to initialize. Those are all called algorithmic specific parameters we have to initialize. Then calculate in objective function, because objective function, that is important thing, no? Because in the preparation of coffee, I told that is a taste is objective function. So all these variables we have to put in objective function. If your objective function is good, that is if you got the satisfied value, then you can terminate the algorithm. If not, then update position and velocity with the help of those equations. And after that, then what we have to do, calculate again fitness value in the objective function. Then if it satisfies that one, then it's okay. If that is not the case, then again go for the next iteration. So that is how it will work here. So then we will take one example. I think by time is 11:20. Sir, HOD sir, are you present in the meeting?
Sir,
Sir, up to can I take can you please tell me what is my time limitation here up to the time?
so
11:40, 11:50 or
11:45, sir. You can
okay, fine. Because I have I will concentrate on this one, which will take some time. Okay, fine. Quite good.
up to 11:45, sir.
Yeah, fine. Right. Let me take one simple problem. I think everybody knows the answer of this one. There is no need of any calculator or something like that. The first one is I am taking one manual example, and we will see how step by step we can take this. We'll solve this problem. So in order to solve this problem, please take a snapshot of that equation. If you're interested, please join with me and solve the problem so that you will get some sort of hands-on feeling of solving the problem here. So this is the objective function here. This is minimization of f of x. I am taking in a simple example. You can implement for your case. X minus 7 whole square. That means I want to minimize the function f of x. I want to minimize the function f of x. Objective function is different. Variable is different. Please remember that. This is objective function. This objective function has to be minimized. Minimized at one value of x. Then only it will be minimized. Listen that one. This is f of x is objective function. This function has to be minimized. So when it will be minimized, this will be minimized at one value of x. That x should be greater than 0. That x value should be greater than 0. Then only it will be minimized. So that means you have to find out the value of x in order to minimize this function here. I think everybody will tell this answer here. So the value of x is equal to 7. Everybody will tell this answer here. So x is equal to 7 means then if you substitute in f of x, then what you will get here? 7 minus 7 whole square. So then what happens here? F is equal to 0. That means the function is minimized. The function is minimized at a value of x is equal to 7. So that means in your algorithm here, let us say a PSO algorithm, if you are implementing now, you have to find at the end, you have to find out the value of x as 7, maybe near to 7. I told you, these PSO, all these algorithms, they won't give you exactly minimum and maximum values. They will provide you the values which are near to 1, near to the minimum value or near to the maximum value. You may not get exactly at 7. You may get at 6.888, 6.9999, 7.1111. You may not get exactly at 7. But if you go for NR method, then you will get it. Easily will get it, that one here. So that is how we have to find out here the values here. So then we will start our search. Then what we will do, that we will see here. That means how we can solve this one, that we will see here. Suppose if you go right. Suppose if you go in numerical methods, differentiation, you can differentiate this one. I think maybe in first differentiation or in second differentiation, you will get the value of x. That everybody can do this one with help of numerical. Exactly the value of x is equal to some 2x is equal to something 14 like that. You will get it. I think you will get the answer, exact answer. You will get it. 2x is equal to 14 and x is equal to 7. You will get it. But in the case of PSO, we will see how we can implement it. What is the first step in our case? We have to initialize the population. That is the first number. That is the first step. So let me see the first step here. So what is the constraint we have to consider here? X should be greater than 0. That means I can take any value which is greater than 0. I can consider x is equal to 99 also. X is equal to 40 also. X is equal to 5 also. 5.4 also. But it should be greater than 0. That is one constraint they have given. So the first thing is I am generating the population. Let us say for our convenience, we are generating the population between 0 to 10. Any number you can take it. You can practice simultaneously by taking any number which you want. But for our convenience and common understanding, I am taking the values as x1 as 2.24, 2 this is one bird, bird 1. And this is another bird, this is bird 1, bird 2. And this is the third bird, 3, and next bird is 4. So in our population, I have considered 4 birds. The 4 birds, they are having initial positions. What is the initial position of this one here? 2.234, and B2 is equal to 9. I told you, we have to give initial position. Otherwise, randomly we can generate with help of MATLAB coding. We can generate it. That is a different issue. But our understanding, that means we have to initialize it. So randomly we have initialized it. A random that code is there in the MATLAB, then we can get these values. Let us assume we got these values as a 2.234, 9.547, and 4.214 and 5.645. So what is the next step we have to do in the algorithm? Can you please go to the algorithm here? You please take this snapshot of this algorithm also. If it is required, please take the snapshot of this algorithm also. So once we do that one, we have to put it in a objective function and we have to find out the values. So what is the objective function here? This is the objective function. We have to substitute all the values of x and we have to find out the values here. So that means x1 we have to substitute there. x2 we have to substitute there. That means in x minus 7 whole square, no. This is x minus 7 whole square, no. So in the place of this one, you substitute this one and tell me the value. And x2, again same thing. x3, again same thing. And x4, again same thing. That means you will get the function values here, f of x. Suppose in any iteration, if f of x is equal to 0, then what happens? Already you reached your minimum. That value should be your minimum. But in this case, you won't get that value here. So I have substituted that one. Then evaluation fitness values. So each value, because f of x1 is substituted there. So if you substitute that one, what you will get here? What is the value we're getting? 2.234. So what you will get here? So this is nothing but 2.234 minus 7 whole square. So 2.234 minus 7 whole square. I think this value is 22.71. Similarly, you can take another values here. What is another value here? Can you please tell me how many variables are there here in this equation? So, can you sign the answer for that? Can you please tell me what are the variables are there in the chart box? I would like to ask that question here. How many variables are there in your function, objective function? Can you please answer this one? Anybody in the chat box here? In the just now we have shared this one, x minus 7 whole square. In x minus 7 whole square, how many variables are there in your objective function? Can anybody answer that question in the chat box? Variables. Yeah, very good. Only one variable. Very nice. Very nice. So only one variable is there. But we are considering the population here. 4 birds we are considering now. Very good. 1 minute. Current slide. Right. Right. So that means you have to substitute that one here. I think you will get 22.714. That is a thing that you will get here. And similarly, do the process. What is x2? X2 you have to substitute. Whatever the value is there, x2 you substitute that one. You will get 6.48, something like that. And substitute that one, another one here, x3. You will get 7.761. x4, it's okay, fine. So now you please see this one here. See this one here. I would like to ask one question here. This is the first iteration results we are having now. What is the first iteration? We have randomly, we have generated the population and we have substituted these values in the function and we have updated the fitness values of this one like this. Our desirable value is equal to f of x is equal to 0. Actually, that is our minimization, no? Function minimization. So please remember this is a minimization problem. So can you please tell me here, which is the global best in this equation? Which is the global best in this one? What is the global best here? What is the global best in this after first iteration? What is the global best of the particle here? Can you please think in the chat box? Global best in this one, because please see here, I will scroll under slide also. This one, 1 minute. 1 minute. So what is the particles we have assumed here? Right. So these are all the particles that we have assumed: 2.234, 9.547, 4.214, 5.647. Among all this, we have substituted in the function, and the function value we are getting here is 22 point something, 6.48, 7.76, and 1.83. Among all this, next step what we have to do is we have to identify what is G best in this iteration. That is the first thing. All personal bests are best for them only. P bests are same. For this x1, P best is its own position. For x2, P best is its own position. For x3, what is the personal best? Its own position, because it's a personal thing, right? x4, the personal best is its own position here. So similarly, next one is, this is a C here. What is the D best here? 5.645. Why? Because it's a function minimization. Function minimization means that means we have to minimize this function. So the lesser value we are getting here, that is your G best in your first iteration. So now you have identified for entire swarm of 4 birds which are present here, the best one is 5.645. That is the first thing. Whatever the P best is every best is for the P best only. That is P best of this one is 2.234. P best of this one is 9.547. P best of this one is 4.214. And P best of this one is 5.645. This P best and G best are same. Please remember, because our answer you know already in your mind, it is 7, right? So when compared with all those things, which one is near to 7? 5.6 is somewhat near to 7. That is why the function minimization value is this one here. That means after the first iteration results, listen very carefully. X4 is better now. The X4 particle is better. X4 particle is better. But that is the beauty of this algorithm when compared with the genetic algorithm. Genetic algorithm, no survival of the fittest. Suppose if this one doesn't perform well, then it cannot participate in the next iteration. But here you see, after first iteration, X4 is producing better results. Then I will go the next process here. What is the next process I have to do? Then I will tell you, please remember this one. X4 is best in the first iteration. In the second iteration, we will see which one is best. Then we will discuss the particular point there. Then what is the next one we have to do? In the same example, those fishermen, they updated themselves, right? What they have updated? They have updated the velocity and the position. Okay. Velocity equation, I told you to take a snapshot of that one. Please take the velocity equation. And also the position equation we have to do. And I told you some algorithmic specific parameters we have to consider. That one is C1 is the cognitive value and C2 is the social value. Just you consider that is 2. And random values as so and so. You can consider any random value between 0 to 1 as you like to process this algorithm. Right. So all initial positions, because there is no initial position, we have to consider initial position is 0 because they are at the starting position, right? Now initial positions are 0. Then we will see here the first one, how we will calculate here. I will tell you. So what is the first particle we are having? 2.234, right? 2.234. For 2.234, what is the global best? Global best is for the entire swarm, 5.645. What is the personal best of this first particle? Its value itself, that is 2.234. Now we please see the velocity equation now. The velocity equation is equal to, this is the initial velocity, C1 value, C1, C2 equal to 2, I told. Random value, any random value between 0 to 1. For our convenience, just take these values. And X best, that means X particle P best, 2.234 minus X1. X1 is also same. This is also 2.234, 2.234 minus 2.234, right? Plus C2 is 2. And the random 2 is random number 0.3287 into global best. The global best is equal to, what is the value here? 5.645 minus X1. What is X1 here? 2.234. How it has to update? Please remember here why it is 5.645 minus 2.234. One person, A person who is catching fish, he has to update himself with reference to B, because B is performing better. So that is why 5.645 minus 2.234, because it has to update. So then I think you will get the value of this one as 2.2423. 2.2423. That means it has not updated much. 2.23. This is the velocity you got here. This is velocity, sorry. This is only velocity. Now after that we have to find out the position. How we will find out the new position? Velocity plus old position. What is the velocity here? 2.24 plus what is the initial position? 2.234. 2.24 plus 2.234. You will get 4.47. What is your desired value actually? 7, no? So you see this algorithm in next step, it is moving towards the positive side. That means how it is converging, you please see here. You have to substitute in the flow chart. So what are the new positions we are getting now? The new positions we are getting here is, you see here, this is 4.47. And this one we got here, not solved here. 7.8, 4.48. Yeah, new position we got here, 7.8 we got here, and 4.48 we got here, and 5.645. It remains same because it's a global best, right? That is same. So after the end of the second iteration, you'll see the values here. This is the values. What are the values we are getting here? 4.47, 7.8, 4.48, and 5.645. So this is how we get the values here. But if you substitute in the fitness value, in that objective function, you see here second bird, let us say, the value is equal to 0.067. 0.067 means almost it is 0. It is almost 0. That means in the second position, there is a significant drop in the fitness function. You can go for the step 3 also, no issues in that. But in the second iteration, what you can understand here, almost your second value, that is nothing but second bird, is now it's approaching the near global solution, because you know the value is equal to 7. It is 7.8 now. So that means in the first iteration I told X4 is superior. That is the global best, right? X4 is superior. But in the second iteration, now X2 is superior. Now can you please identify global best at this condition? Now the global best is 7.8. What is the 7.819? Now the new global best you are getting now. This is new G best. That is 7.81. So that means now again you have to do the iterations if you want. If you're interested now, then you can do iterations here. So that means the beauty of this algorithm is, even though one person, that means what we can call in one iteration, the solution may be weak, but there is a significant amount of chances that it may improve its value further in the next iterations. So I stop the iteration here. It's no, that means, but you can go for the iteration. I think you will get another iteration, you will get the value of 6.999, something like that you will get, or otherwise 7.111 like that you will get here. So that means in these algorithms, I think anyhow, this algorithm is very simple. It is updating with velocity and also this equation is what we can call the velocity equation and also the position equation. So, but the important point that we have to understand here is, if you look into this figure, which I have already showed, sorry, 1 minute. Right. Right. You see here, one interesting point here is, let me everything here. Okay. You see here, this the person B, he has reached to this point. Actually, what is global minimum here? This is global minimum. You can see here, this is the big dot mark which I am putting here. This is the global minimum actually. But the person B has not reached the global minimum. He has reached to this point. That means, let us say this is 7 value, numerical value number. So this will be somewhere 5.5 or 7.11 or 6.99. That means the point which we have to observe here is they are all near global optimum solutions. That is important point here. Not global optimal solutions. Near global optimal solutions. All these nature-inspired algorithms, they will provide you the values of near global optimal values, near global values, near values, not exactly values. But if the same problem, if you solve by differentiation method, then what you will get, I think in the second derivation, you will get the answer, I think. Maybe in the first also you will get it. That is exactly 7, you will get it here. So that is a beauty of these iterative methods. Exactly what is the global minimum if your search point is right. That is the question here. If your search point is wrong, then very difficult. Suppose, let me take you another case study so that you will understand it in better way here. Let us see how we can implement in one application of electrical application. So I want to control one inverter. What is the inverter and what are the types? I don't want to tell here. So one inverter is there. Let us say this is one inverter, cascade HP level inverter, which is used topology in some medium voltage drive applications. Our objective is to control the inverter. That is the thing here. I want to control in such a way that all the firing angles are less than 90 degrees. That is nothing but a constraint. I want to control the inverter with minimum percentage THD. That is my objective function. I think it is very clear for you. Objective function is minimum THD. What you have to find out here? Switching angles you have to find out here. So how to find out what is the constraint of the switching angles? All the angles are 0 to 90 degrees. Now tell me, suppose if I go for Newton-Raphson method, if the switching angle is in between 0 to 90 degrees, can you please tell me how many angles are present here? 0 to 90 degrees. 0.1 is also one angle, 0.3 is also one angle, 1 is an also angle, 23.4 is an also angle, 89.999 is also angle. How many angles are there here in between 0 to 90? Infinity. Suppose if infinity angles are there, what is the probability of guessing a right angle in a Newton-Raphson method? Because it needs an initial guess, right? It is very difficult to guess like that. That is why we are going for these algorithms. That is the necessity of going for these algorithms here. So let me tell you, I told you 3 steps, right, to implement it. What is the step 1? Step 1 is objective function development. I told you the same structure I am considering so that it will be easy for you to understanding. Step 2 is finding out of algorithm. I told you what are the steps that you have to follow while selecting the algorithm. I told you freelance theorem. There is no good algorithm. There is, and another one is step 3, validation. You have to validate this one here. Let us say this is the general structure of drive system in one medium voltage drive system. I don't want to tell everything here. This is a place where inverter come into picture, because now to control this induction motor, we need to vary the voltage and also the frequency. In some cases, we have to keep V by F ratio as constant. Below rated, above rated frequency, we have to keep the ratio as constant. Below rated frequency, we have to increase the V by F ratio. So there are some certain situations where you have to control your inverter. Suppose if you want to control this, the flux plays an important role here. If you want to control this induction motor at below rated frequency, V by F ratio has to be increased. And after that means rated frequency, V by F ratio has to be kept constant. So that is how flux varies and everything. I don't want to tell here, but that is important parameter here, V and F. So in order to obtain a variable voltage, what we can call desired magnitude of AC voltage at desired frequency, that is the inverter, not a DC to AC or something like that. A desired magnitude of voltage at desired frequency. So this is a place where we are using this inverter. So this inverter has to be controlled. That inverter configuration is I told. So these are the list of various companies across the globe who are using this inverter here. You can see here inverter configuration, multi-level inverter, cascade H-bridge inverter, flying capacitor inverter. These are all different manufacturing companies across the globe which are using this inverter here. So anyhow, I have taken one inverter, let us assume. This is a practical, if you want to see, this should be the entire casing will be like this, not a small box like that. This is it occupies entire big room, it will occupy here. Some cooling arrangement will be there, something like that it will be there here. The point here is, suppose if the rating of the inverter is very high, suppose if you are operating at a megawatt level, suppose in medium voltage drive operation, just now I told here, this operating is in terms of megawatts, you can see here, it may extend up to 100 megawatts also. You can see in lift irrigation pumps also, the motors is in terms of megawatts only, 100 megawatts, something like that. Suppose if you are operating at that higher something like that, then what about the switching losses? The switching current will be high, switching losses will be high, heating, more amount of heat will be produced. That requires a cooling requirement also increases. This is a place where cooling requirement is there, the box which I have marked here. So that means, suppose if you are using a high switching frequency modulation technique, let us say high switching frequency, carrier-based methods, something like that. If you are operating your inverter at higher levels of megawatt level of voltage, power level, switching losses will be high. Then cooling requirement, this is called cooling requirement. No, this unit also increases. This is an inverter module. This is the place where we are concentrating, inverter module. So let us say one observation is, I want to control the inverter at low switching frequency to reduce some sort of losses. This is the configuration. So in each phase, we are having 20 switches are there in this configuration. 20, 20, 20, 60 switches are there. These 60 switches we have to control. So 1, 2, 3, 5 bridges. Let us consider one bridge is fired at alpha 1 and alpha 2. Let us say alpha 1, not alpha 1, alpha 1, and let us say first bridge. Next bridge is fired at alpha 2. Next bridge is fired at alpha 3 to produce this voltage. Next bridge at alpha 4, next bridge at alpha 5, and remaining bridges are 120 degrees apart from each other. That is how the philosophy of kind of firing this one here. So the point here is, if you apply some Fourier series for this waveform, this entire waveform, Fourier series, then you will get one equation. These equations are nothing but, these points are nothing but alpha 1, alpha 2, and alpha 3, alpha 4, alpha 5. So these are all variables in our problem now. Variables here is just like a coffee powder, milk variables here. In my problem, these alpha 1, alpha 2, alpha 3, alpha 4 are variables. So I have to find out those variables by satisfying the constraints. What is the constraints here? This is a odd quarter symmetry is there. No, this one is less than 90 degrees. Total symmetry is there here. So that means alpha 1 should be less than 90 degrees, alpha 2, similarly alpha 3, like that in a such a way that alpha 1 is less than alpha 2 is less than alpha 3 is less than alpha 4 is less than alpha 5. So that is the order also. So alpha 5 is higher compared to alpha 4, alpha 3, alpha 4, alpha 5. So I have to write the Fourier series. A periodic repeating waveform can be expressed in terms of Fourier series. A0 by 2 plus summation n is equal to 1 to infinity n cos n of omega t plus bl sin omega t. Then if you write like this, you will get this expression. This is the expression you will get here. This is the Fourier series expression. So this expression, all these higher order harmonics that we have to equate to 0. This is a fundamental component. We need a fundamental component. This one is fundamental component. These are all other harmonics we are equating to 0. That means because particularly the lower order harmonics will damage the power system to a higher extent when compared with the higher order systems. So this one we have to equate to 0. So this is the non-linear problem we are getting. Please remember, all these non-linear optimization problems are solved by these optimization techniques. Whenever you are getting some machine learning algorithms also, non-linear nature of finding all the things, then you will use all these algorithms only. So this is a non-linear transcendental trigonometric equation. Non-linear, not linear equation, non-linear equations. Then our objective is, we have to eliminate all these higher order harmonics, 5th order, 7th order, 11th order, 13th order, and we have to produce highest magnitude of fundamental voltage with less percentage THD. So our objective function is less percentage THD. Variables is alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Constraints is all are less than 90 degrees in such a way that this one is alpha 1 is less than alpha 2 is less than alpha 3 is less than alpha 5. So I think now the objective function has been formulated. That is why I told this step 1 is completed now. For any research problem, this is the first thing we have to do. Almost all 80% of the problem is over after finding out of this one. Then what we have to do? Then you go for the algorithm, PSO algorithm. You have to initialize the population. What is the population here? I have used 1,000 birds. What is the random switching angles? You can take any random switching angles in between 0 to 90 and gives a W value, C1 value, C2 value. Then you have to find the initial fitness value. Then after that, we have to update the velocity. After that, you have to update the position. Then you will find the new switching angles. Again, you substitute new switching angles in this objective function, whether it is feasible or not. If not, again, you go for next iteration and the process will continue in MATLAB code. Then after that, you will find the solutions here. Then how it can be implemented? You can see here, the same algorithm, the same problem I have solved by using Newton-Raphson algorithm, that is NR algorithm, that is gradient-based approach here. In a gradient-based approach here, you please see here, this is a place where there is no solution. These are all switching angles. These dots are there, no. This is the blue one and the green one and red one and light green one and this velvet color. These are all switching angles. What are the switching angles here? Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. These are all switching angles here. Different modulation index, I have find out the switching angles here. I found the switching angles at different modulation index. You please see here, at a lower range of modulation index, there is no solution. At higher range of modulation index, there is no solution. Usually for a variable speed drive applications, you have to vary the voltage from, that means the minimum voltage to the rated voltage also. But here in the modulation index 1 or a higher range of modulation index, these limitation of Newton-Raphson method cannot control your inverter because you cannot find out the switching angles here because it is in non-linear nature. Because of non-linear nature, there is a possibility at one particular modulation index, there is a possibility of getting a solution or not getting a solution or multiple solutions. That will be like that. That is a non-linear nature here. So if you see this NR method, it cannot give solutions here. So now that is the beauty of these algorithms here. You see here, this is some percentage THD values you got with the help of the algorithm here. So you please listen here. These are all calculations. Don't worry about it. The minimum percentage THD you got is 5.33. Please see the spectrum of percentage THD here. This is a FFT analysis you can see here. Almost all the lower order harmonics are minimized completely to a greater extent here at a modulation index of 0.755. Percentage THD is equal to that means I cannot control my inverter at minimum percentage THD at a modulation index of 1. Actually, what is our objective? Our objective is to control inverter at highest by producing highest magnitude of output voltage. But you cannot produce a magnetic output voltage at minimum percentage THD. That means at 1, I think it is unable to, it could not provide the solution at the modulation index of 1. That is the one reason here. But the minimum percentage THD has produced at 5.33. Please listen, observe very carefully this graph because there is advantages of gradient methods, there is a disadvantage of gradient methods. You cannot get the harmonic spectrum with this much of, that means clean when compared with these other methods here. Then you see here, this is implementation in PSO method. In the PSO method, almost all complete range of modulation index, this method has solved the problem. That means solve the problem means it has obtained the solutions alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. So in your work also, first you have to go with the normal method, then you have to compare with this method here. Otherwise, no, then you cannot do that comparison. You never know what is the reality of otherwise importance of these numerical methods here. So that means successfully it has compared, solved this one here. Then these are all the table column here. You see here. So at modulation of index of 1, the percentage THD produced is 4.10. That means when compared to that one, so this algorithm has produced a better results here. So you can see here, even though this is 4.10, you can see here this one and this one the harmonic spectrum is not so clean when compared with this NR method here. See here, NR method is very neat, but when compared to that one, it is not so good. But we need a solution, right? Because it is unable to control that one at modulation index of 1, but this method can control this one at modulation index of 1. So these are all these line-to-line voltages and everything here, phase voltages here. So this we can implement practically also. How we can implement practically? I will tell you in 1 minute and then I'll close the session here. So this MATLAB coding will be used to run that one, coding that switching angles will get here. With the help of the FPGA based Xilinx controller. And because here we're having 60 switches are there, no? Because we have to go for higher end to produce the signals here. That is why we can use a FPGA based pattern controller. So that one is given to the switching angles here. This is the inverter, right? And the output voltage is observed in this power analyzer here. So that means we need some sort of these FPGA, depending upon the switching, that means switches we are using here. If your number of switches are very less, it's okay. If we are going for these higher ones, no 100 switches, then you have to go for these FPGA controllers. Then at each modulation index, the program is run, and we have find out those switching angles. Those switching angles will be given to this inverter. Inverter is that means percentage THD and everything will be taken in that power analyzer here. So this is a practical simulated wave, practical waveforms. This is a line-to-line voltage waveform here, line-to-line voltage waveform here. And this one is the harmonic spectrum we are getting here. So I think there is some difference will be there. That means practical and simulation and everything. So that is okay. But it got a good harmonic profile. Maybe this one is some 5.2 something like that. So it's not visible here. It's some 5.2 something like that. It's there. So this is the same modulation at the modulation index of 1. We have taken this one here. So that means one important point that we have to observe here is the first point is there is no guarantee of finding of optimal solution in finite time. That is important. Sometimes it will take more time. Suppose if you run genetic algorithm, the same problem I have solved by using genetic algorithm also. We won't get consistent results. The same problem I have solved by using TLBO algorithm. So there is no guarantee that we will get same. That means the algorithm is not consistent and rugged also when compared with the PSO algorithm. The next one is a number of parameters. I told you algorithmic specific parameters. So algorithmic specific parameters are more here that we have to taken care of. Why we have to consider C1 is equal to 2, C1 is equal to 1. So this is all random error only. There is no thumb rules why we have to consider C1 is equal to 2. Just go and run your algorithm with your results, and you have to, with literature, you have to find out that one. So you can do some sort of experiments there. Maybe if you consider C1 is equal to 1 and C2 is equal to 1.5.
Yes, sir. I'll take your mail ID. Yes, sir. Thank you so much. Thank you, sir.
Yes. Thank you.
Thank you, Ekta ma'am, for your query. Sir, one more query is in the chat box, sir. So that's
Yes,
a query given by one of our participants.
How to fix the values for optimal optimization parameter? Values means these algorithmic parameters you were asking.
Yes, sir.
Sir, this is nobody can answer this question. This is all lottery only. This question cannot be answered here because these are all random. Because that is why it's called probabilistic approach methods. So you have to sit and you have to use so many values, vary the values, run your algorithm, find the solution. At one point of time, you will get optimal values. It is your that means what we can call your hard work only. That one. Got it? No, but some sort of guidelines you will get from the previous researchers. That's why I told why we have to consider C1 is equal to 2 and C2 is equal to 2. Actually, I consider C1 plus C is 4 in my algorithm. But, so there is no thumb rule that exactly is well should be considered for algorithmic specific terms.
Sir, one more question is this, sir. In the chat box.
Yes, sir.
PSO is equal to fall into the local optimum in high dimensional space, and as a
Understand what actual implementations have been done. So thank you so much. I hope all the participants have cleared their doubts, and if you have some more doubts also, sir is ready to answer through his mail. So please take out the mail. Sir, from our management side and from my department side, I heartfully thank you, sir. Sir, we need your cooperation in future also, sir.
Thank you, sir.
Thank you
Welcome for your for inviting me here and giving me a nice platform to exchange my ideas. So, thank you once again.
It's our pleasure, sir. Thank you, sir.
Thank you, sir.
Dear participants, thank you for attending this session, and one more session will be at afternoon. Please be there by 2 p.m. Thank you so much.